Section 5.5b is on using z-scores to determine percentages. So once we have a z-score, we know about where it is on the normal distribution curve, where that data value lies in relative to the mean on the normal distribution curve. And we can use a z-score table then to figure out the area under the curve to the left of that z-score, which is also can be interpreted as the percentage of data to the left of the z-score, or the probability that a randomly chosen piece of data is to the left of that z-score. So the z-score table, there's a piece of it just shown down below here, but it basically gives you the fraction of data that fraction data with z-scores that are less than the particular z-score that you have. So, for example, if you have a z-score of 1.27, to look that up in the table, you would first look in the first column to get the 1.2, and then you'd look along the columns across the top until you got the second decimal place of 7, and so you can see that you just move along here until it matched up with the 0.7, so that will give you together, that makes 1.27, and this value here of 0.8980 represents the fraction of the area of the curve that is to the left of that z-score. It can be written in using this notation: A in brackets the z-score, so in this case it'd be A with the 1.27 in the brackets, and this value 0.8980 represents a portion of data that's to the left of that z-score, has a z-score value that's smaller than 1.27, and if you want to convert that to a percent, you'd multiply it by 100%, and that would give you 89.80, or almost 90% of the data has a z-score that's less than 1.27. So that would mean almost 90% of the data is less than that particular data value that you have. Okay, so it's going to be a little bit difficult to explain these questions here because I don't have a z-score chart on this page. I can't flip to one for you to see, but we'll try our best. If you don't have a z-score table, you can't do these questions. So you do need a z-score table. Anyway, we'll just try our best and see if you can follow along. So the first one says determine the percentage of data to the left of a z-score of negative 2.04. So if you've got your z-score table, look at the negative side, the negative z-scores, and find negative 2.0 in the very first column, and then go along the row until you get to 0.04, and you should have a z-score table value of 0.0207. So we want to write that in the notation A of negative 2.04 from the table is I forget what I said, 2.0207. Okay, and if we're looking at kind of this normal curve over here, negative 2.04 would be somewhere around here, just approximates down to the left of the mean and kind of low in the lower end of it, because it's a little bit more than 2 standard deviations below the mean. And this percentage, this value that we've got here, this decimal, represents the area under the curve to the left of that z-score value. So as a percentage, that would be equal to 0.0207 times 100%, which would be 2.07%. So 2.07% of the data would have a z-score value less than negative 2.04. Okay, question number 2 says determine percentage of data to the left of a z-score of 1.26. So the area under the curve using the table, if we go to the positive z-score table and go to 1.2 in the very first column, go down to 1.2, and then go across the row until you get to the decimal 0.06, and that should have a z-score value of 0.8962. 0.8962. So if we just kind of draw 1.26. That's a positive z-score, so it would be a little bit more than 1 standard deviation above the mean, so approximately just a little bit above the mean here. And this value that I'm getting on my z-score table represents the area to the left of that z-score. So that would be the same as basically multiplying by 100% is the same as moving the decimal place 2 places to the right. So that if we multiply that by 100%, we're going to get 89.62% of the data is to the left of a z-score of 1.26. And number 3, determine the percentage of data that's to the right. Now this time it's to the right, but the table only shows to the left. So we're going to find the value to the left of 1.2, and 1.2 would be about right here, roughly above, probably a little bit closer than that, but and this is what we want. But when we go to the z-score table, this is what we're going to get. We're going to get 1.2 says here, but we're going to get this, we're going to get to the left. So if we find 1.2, we'll go to the positive table again, and we need 1.2 in the first column, and because there is no second decimal place, that means we match it up at 1.20, so the very first one in that row, which is 0.8849. Now that represents the data to the left, so we want 1 minus 0.8849, because 1 is the same as 100%, that's the decimal form of 100%. So if we take 1 minus 0.8849, we get 0.1151, or 11.51% if we move the decimal place 2 places to the right, multiply by 100% in other words. So 11.51% would be the percentage of data to the right of the z-score. But we did have to use the table value of the value left of the z-score first, and then subtract it from 100% or 1 if we're using the decimal form. Number 4, determine the percentage of data to the right, again, of the z-score. So if we get a of negative 0.76 from the chart, again, we want negative 0.76 would be probably somewhere around here. And we want to the right, so we want all of this. But the table, we can only work with the table, which is going to give us the opposite of what we want. So if this is the mean, negative 0.76 will be close to that, but on the left side, the table is going to give us this region right here. So using the table, if we go to negative side of the table and negative 0.7, and then match it up go along the row until you get 0.06, it would be 0.2236. 0.2236. That's what's on the table. That represents the percentage of data, or the area of data to the left of the z-score. So we want 1 minus 0.2236 if we want the area to the right. So that would be 1 minus 0.2236 is 0.7764, which is 77.64% of data is to the right of negative 0.76. And that kind of makes sense because we know that 50% would be above the mean, and if we're a little bit below the mean, it should be a little bit more than 50%. So around 77.64% seems reasonable. Okay, number 5, what happens if you're looking for a percentage of data in between two values? Well, here you've got two z-scores which are pretty close together, and they're on the negative side, so on the left of the mean. So we have like 0.56, negative 0.56. Well, actually I'm going to call that negative 0.4. So I don't think I can get any closer on the other side. And this is going to be negative 0.56. So they're pretty close, and if you're looking for the data between, you'd want like that strip between those two lines that I just drew. So when we look at the z-scores, it gives us data to the left of those two values. So I'm just going to exaggerate over here a little bit. If I draw a curve, and here's my mean, and I want, if I take the first one, which was 0.04, and I find everything to the left of that from my z-score table, and then I'm just going to use red for a minute, and if I take the point, look up at the point negative 0.56 on the table and get everything to the left of that, I'm going to get this. So basically, if I take the black, which is underneath the area from here down, and then I subtract the area of the red, I should be left with the piece that I want in blue there, that section. So that's basically what we have to do here. First we have to find the area of each of those z-score values. So that would be from the table negative 0.4. So you'd go to the negative side of the table, negative 0.40 would be 0.3121. No, sorry, that's 0.3945. So 0.40, you got to go right over to the very last item in the row, and that would be 0.3446. 0.3446, and then we want the area under the curve for negative 0.56, so that will be negative 0.5 in your first column, and then go along the row till you get to the 0.06, which is 0.2877. And then if you want the area between, you would want the A of negative 0.4, subtract the one that's further away from the mean, negative 0.56. And you know you're doing this right because you should end up with a positive when you subtract them anyway. And when you take the area of negative 0.4, you get 0.3446, subtract 0.2877, which is going to give you 0.0569, or 5.69% if you move the decimal place 2 places to the right. Basically same as multiplying by 100%. So about 5.69% of the data lies between the z-scores of negative 0.4 and negative 0.56. And similarly for question 6, we can find the area for the z-score of 0.34, which if you check on your table, 0.34 would be 0.6331, and the area that goes with 2.15 on your table would be 2.1, go to the positive z-score table, 2.15, go along, find the column, in the column 2.1, and then go along to 0.05 till you get 0.9842. And visually what we're looking for is 0.34 would just be above the mean here, and 2.15 would be a fair bit above the mean, and this, you'd be looking for this portion here, the stuff in between. So this would be basically 0.9842 subtract 0.6331, which is 0.3511, which if you multiply that by 100%, move the decimal place 2 places to the right, would give you 34.11% of the data would lie between those two z-score values. Okay, question 7. IQ tests are normally distributed with a mean of 100 and a standard deviation of 15. So we're asked to draw a normal distribution for this situation. So this is going back to like what we did in section 5.4. So this would be 100. I'm just going to draw my lines first. This is 1 standard deviation, 2 standard deviations, 3, and this would be 1, 2, 3. So this one would be plus the standard deviation, so 100 plus 15 would be 115, then plus another 15 would be 130, another 15 would be 145. And then going the other way, 100 take away 15 would be 85, take away another 15 would be 70, take away another 15 would be 55. So this would represent 34% and 34% and 13.5% and 2.35%. And this one was 0.15%. And this was the 13.5%, 2.35%, and 0.15%. That's a 3, doesn't look like it, but... Alright, so it says, question B says, what percentage of students achieve less than 130? So if you use the 130 is one of the labels on the curve there. So if you use your percentages here, we know that up to the mean, if you add all those up, it's 50% of the data is below the mean. So basically it would be 50% plus you got these two sections here, which is 34%, and another 13.5%. So if you add all those up, you get 97.5% of the data. So now if we take the same question and do that using z-scores, we know that the z-score for 130, remember our definition is x minus the mean over the standard deviation, and in this case it would be 130 minus 100 over the standard deviation was 15, and that would give you a z-score of 2. So if we check from on the chart, and we look up 2.0 on the 2.00 on the chart, we get 0.9772. So A of 2 would be 0.9772 or 97.72%. So you can see that it's approximately very close, 97.5 versus 97.7%, 72%. Alright, so the second question, so you can see, like I said, the z-score chart, even if you could use this kind of a table like we have up here, even if it is a label on that, you can still get a fairly accurate or probably even more accurate answer using the z-score chart. Alright, so the next question, what percentage of students achieved a z-score of 120 or higher? Well, 120 is not on the table as one of the labels up there, so we have to use z-scores for this one. And the z-score would be 120 minus 100 over 15, which is going to be 20 over 15, which is going to be 1.3, I think. Yeah, 1.3 repeating. So it's 1.33 if we use 2 decimal places. So that's approximately. So if we check our z-score table, we get the area for the data, percentage of data to the left of 1.33 would be 1.3, and then go over to 3.003 on the table would be 0.9082. Now that represents the data to the left. We need 1 minus 0.9082 because we want it to be higher, 120 or higher, so that's going to mean to the right. So 1 minus 0.9082 is 0.0918, or if you put the decimal place over 2 places to the right to change it to a percent, that would be 9.18% of the data. So 9.18% of students scored 120 or more. Okay, question 8. The speeds of cars on highway have a mean of 80 kilometers per hour with a standard deviation of 8 kilometers per hour. What percent of the cars average more than 96 kilometers? And again, we can use z-scores for this problem. So the z-score for 96 would be 96 subtract the mean of 80 over the standard deviation of 8. And that's going to give you 16 over 8, which is 2. And we did that one a few minutes ago on the z-score chart, and we know that that's 0.9772. But that will give us the percent of data that's less than 96. We want the ones that average more than 96. So we need, in this case, 1 minus 0.9772 to get to the right of 96, a score of 96. So that would be 1 minus 0.9772, which would be 0.0228, which if you convert to a percent would be, move that 2 places to the right, so that would be 2.28% of cars. So 2.28% of cars averaged more than 96 kilometers per hour. Okay, next question. Battery Incorporated claims its batteries have a mean life of 50 with standard deviation of 6. What's the probability that a battery will last 57 hours or longer? So, if we calculate the z-score for 57, because if this here is 50, 56 would be the next label, which is not what we want. We want 57, and 6 more than that would be 62, so 57 lies in between 56 and 62, so we'll use z-scores, and the z-score for 57 would be 57 subtract the mean life of 50 over the standard deviation of 6, so that would be 7 over 6, which is 1.1666, so on. So that would be, if I round that off to 2 decimal places, it would be 1.17. So if we go to our z-score chart, we will get 1 and look up 1.17. We would get 1.1, move over to 7 would be 0.8790. But again, that would give us less than 57. We want 57 or longer, so we want to the right. So we would need 1 minus 0.8790, which is 0.121, or if you move that decimal place 2 places to the right, that's going to be 12.1%, will last 57 hours or longer. So it says if 45,000 batteries are produced, how many would you expect to last 57 hours or longer? So again, we just figured that out in part A, that we would expect 12.1% of those, of the 45,000, to last longer than 57 hours. So that would be decimal 121 times 45,000, which is 5,445 batteries would expect to last longer than 57 hours. 57 hours or longer. Okay, a lineup for tickets to Salmon Fest has an average wait time of 400 seconds with a standard deviation of 32 seconds. What's the probability that you will wait between 350 and 415 seconds for your ticket? So again, we can use z-scores. So we have the z-score for 350 would be 350 subtract 400 all over standard deviation of 32, and that's going to be minus 50 over 32, and you're expecting a negative z-score there because it's below the average wait time. That gives us 1.56, negative 1.5625. So for using the chart, we need 2 decimal places, so we round that off to negative 1.56. And then we do a z-score for 415 seconds. We get 415 minus 400. The mean over the standard deviation is still 32. And that's going to give you 15 over 32. Which is going to give you, sorry about my dogs, they keep barking, but I keep stopping and doing this over again, and it's taking forever, so you're just going to have to listen to them. So this is going to be 0.47 z-score, and we're expecting a positive z-score for that because 415 is above the average wait time of 400. So if we check on, like basically if you were to draw this on a normal distribution, you're going to get, here's your mean, and negative 1.56 is here, and 0.47 will be there, and you're looking for in between. So you would want A of 0.47, subtract A of negative 1.56. You want the one on the right, subtract the one on the left, and then you'll get the stuff in the middle is what you want. Okay? So this will give you, checking up on the z-score chart, 0.47 is going to give you 0.6808, and negative 1.56 is going to give you 0.0594. And if you subtract those, you will get 0.6808 subtract 0.0594, and that gives you 0.6214, or as a percent, that would be 62.14% would have to wait between 350 to 415 seconds for their tickets. I'm not going to write that because it takes too long to write. And I can't squish it in there. Okay, question number 11. The average playing time of a defense player in the NHL is 17.2 minutes per game with a standard deviation of 2.2 minutes. What's the probability that a defense player will play between 15.6 and 19.2 minutes? So again, it's the same kind of thing. You've got to find the z-score for 15.6 using your formula data value minus the mean is 17.2 over the standard deviation is 2.2, and that gives you 15.6, take away 17.2, divided by 2.2, gives you negative 0.7278 2.2, so on. So it's 2 decimal places, that would be negative 0.73. And then the z-score for 19.2 minutes would be 19.2 minus 17.2 over 2.2, which is going to give you 2 over 2.2, which is going to give you 0.900, so on. So this is going to give you 0.91 if you round it to 2 decimal places. So if you want in between 15.6 and 19.2, you want, again, if you look at in terms of which one is on the right, z-score of, there's your mean, so the negative 0.73 would be here and 0.91 would be there. So you would want 0.91 subtract negative 0.73, the area. So it would be a area of 0.91 subtract area under the curve of negative 0.73. And that would give you, using your z-score table, 0.91 would have a value of 0.8186 from the z-score table, and negative 0.73 would be 0.2327. So if you subtract those, you get 0.5859, or as a percent, that would be 58.59% of the data, or 58.59% of the chance that the defense player will play between 15.6 and 19.2 minutes. So it would be 58.59% chance that a player would play between 15.6 and 19.2 minutes. Okay, so standard deviation is also used in society to influence decisions such as the length of warranties provided by companies and the cost of insurance and quality control and opinion polls and stuff like that. So z-scores, which are affected by standard deviation, play a role in these situations. So consider the following example. It is known that the mean value of repairs due to an accident for a Corvette and a Civic is $3,500. The standard deviation for the Corvette is $1,200, while the standard deviation for the Civic is only $800. If the cost of repairs is normally distributed, determine the probability that the repair cost will be over $5,000 for each car. So if we can use z-scores again for this, because if we calculate the z-score for the Corvette, the z-score for the Corvette would be, we're looking at 5,000 would be the value we want to find the z-score for, and we would use the mean for the Corvette, and the Civic was the same, which was $3,500, but the standard deviation for the Corvette was $1,200. So that means that we've got 5,000 take away 3,500, which is $1,500 divided by $1,200, is 1.25 z-score value for that one. And then the Civic, its z-score that we would use for the Civic would be, again, it's $5,000 that we're comparing it to, or trying to determine the probability for. So that's the data value, minus the mean is still 3,500, but for the Civic, it has a standard deviation of 800. So that would give you a z-score of 1.875, which we would round up to 2 decimal places for the table would be 1.88. So the probability that the repair costs will be over 5,000 is basically we want to figure out what percent of data would be above 5,000, So for the Corvette, we would want to check A at 1.25, which would be 1.25, looking at my chart here, is 0.8944. Now that would represent the data to the left of a z-score of 1.25 or less than $5,000. So therefore, 1 minus that which is 0.1056. And if you look at area for 1.88, you will get 1.88 will be 0.9699. But again, we want over 5,000, so they would have 1 minus 0.9699, which is 0.03. Sorry, 0.03. Let me fix that. 0.0301. So, if we look at in terms of percentage, this here would be the probability for Corvette to cost more than $5,000 for repair would be about 10.56% if we convert this to a decimal, to a percentage. And for a Civic would be about 3.01% chance that, so this would be approximately 10.56% chance, and this would be 3.01% chance that you would have the repair cost would be over $5,000 each. So based on these results, which vehicle would have higher insurance premiums? I would think the Corvette would have higher insurance premiums because there's a higher chance that because there's a greater probability that the repair cost will be more than $5,000. There is a higher probability of the repair costs being over $5,000. Okay, so now we're going to try some questions where we're finding data values using z-score table percentages. So if you're given a percentage, you basically have to work backwards now and convert the percentage to a decimal form, and then look for that decimal form in the z-score table of values, and then find the corresponding. This should be z-score here, and that's SOAR. Z-score for that value by looking at the row and column heading for that value. And then to actually, if you're looking for a particular data value, you'd have to take that z-score and put it in the z-score formula with your mean and your standard deviation and use algebra to solve for the data value. So depending on what kind of question you have, basically you'll be working backwards to get the information that you want. So the first one here says you're given that a z-score, you're looking for the z-score for a situation where 34% of the data is to the left of the z-score. So basically, if it's data to the left of 34% is to the left, that would mean on your table, 34% as a decimal, you divide that by 100 to get it as a decimal, so that would be the same as moving the decimal place. Right now it's after the 4, so dividing by 100 would be moving it to the left, so you'd end up with 0.34. And the table values, if you look at them, they all have 4 decimal places, so we're just going to add a couple of zeros to that to make it 4 decimal places. So we will be looking basically on the z-score chart and looking to find something as close to decimal 3400 as we can on the z-score chart, and they're kind of in numerical order somewhat there, so you can kind of follow the pattern until you get something close to 0.3400. And so I'm down in the negative values, and around, I would think the closest one to that might be the one that goes with a z-score of negative 0.401. Okay, so on z-score chart, you get 0.3409 on the z-score chart, which goes with negative 0.4, and what did I say that was? Negative 0.3409 goes with negative 0.40, negative 0.41. So that would be your z-score. Okay. To do when you don't have the table there, that you can't see the table that I'm using. Determine number 2, determine the z-score for a situation where 24% of the data is to the right. So this time we're looking for the right. So we still want to work with 24%. 24% is to the right. 24% to the right implies that 100 minus 24, which is going to be 76%, is to the left. And we want the stuff to the left to use the z-score chart. So therefore, 76% on the z-score table would show up as a decimal, which would be decimal 7600. We move the decimal place 2 places to the left, and then add a couple of zeros to get 4 decimal places. So we look through our z-score chart values and find something as close as we can to 0.7600. And I'm over in the positive z-score values now, and I'm looking at the row with 0.7 in it, and the closest thing there seems to be 0.7611 maybe, which would be, so on the chart, we go to 0.7611, which has a z-score value of 0.7611 has z-score value of 0.71. So that should have 24% of the data to the right of that z-score. Number 3, a manufacturer of personal music players has determined the mean life of the players is 32.4 months, with a standard deviation of 6.3 months. What length of warranty should be offered if the manufacturer wants to restrict repairs to less than 1.5% of all the players sold? So, when we look at this information here, we would want basically, if you look at your normal distribution curve, if you want less than 1.5%, so that means you say 1.5% of the data, you want to basically the warrant to be everything, the z-score that basically goes with 1.5%. That's what you'd want to figure out, what data value goes with a z-score of that has 1.5% of the data less than that z-score. So the z-score, to get the work from that, you need 1.5% on a decimal, as a decimal would be 0. Move decimal place 2 places to the left, so that would be decimal 0.150. So on the chart, you look up in the chart 0.0150 and those numbers there to see if you can 0150. And that is exactly with the z-score. If you look at the row and the column to get the z-score, you get that has, and the chart has z-score of negative 2.17. Because it's 0.0150 is exactly there on the chart, and it has on the row that goes with that is negative 2.1, and the column is 0.07. So if you put those together, you get negative 2.17. So the z-score is negative 2.17. So then if we use the formula, therefore using the formula, we can figure out the data value that you need. So we know that the z-score formula says that you need the data value minus the mean over the standard deviation. So in this case, our data, we don't know. That's what we're looking for. I'm just going to move that down to the next row here. Hang on now. Oh, don't have a whole lot of room to work with. Okay, so this is, we don't know the data value, but we do know the z-score is negative 2.17. We don't know the data value. We do know the mean is 32.4. And we do know that the standard deviation is 6.3. So we're trying to figure out how many months we should have as our warranty, so that the z-score that goes with that months is negative 2.17, and that would mean that only 1.5% would be less than to that particular last any less than that particular time. So then this here would be negative 2.17 over 1 equals x minus 32.4 over 6.3, and then we can cross multiply and we get x take away 32.4 equals 6.3 times negative 2.17. So x take away 32.4 equals negative 2.17 times 6.3. Might help if I turn down the calculator. 6.3 times negative 2.17, which is negative 13.671, which is x is negative 13.671 plus 32.4. So if you add that on, 32.4 onto that, you get 18.729. So basically 18.729 months would have a z-score that's negative 2.17, which would mean that only 1.5% of the data, approximately 1.5% of the data, would be less than 18 months, so that you should offer your warranty to be about 18 months, so that you would make sure that only about 1.5% wouldn't last 18 months and you would have to repair them. So approximately 18 months for your warranty. You round that off to the nearest whole month. Well, technically, numerically that would go up to 19, but if you want to be safe, you don't usually have like a warranty of 19 months. 18 months usually sounds a little better. Okay, question number 4. Running shoes lose their shock absorption after a mean distance of 640 kilometers with a standard deviation of 160 kilometers. Zach is an elite runner and wants to replace his shoes when only 25% of people would replace their shoes. At what distance should he replace his shoes? So it says that, again, this is can be used. You can use z-scores again. He wants to replace his shoes when only 25% of people would replace their shoes. So if you think about that for a minute, if Zach is an elite runner and the mean is 640, and you would think if he's an elite runner, he probably wants to replace his shoes before 640 kilometers. So you'd be looking at the 25% would be, he'd be trying to do it a little bit earlier than what most people would. Most people would probably let them go a little longer. So you're probably looking for a z-score that's somewhere down below the mean, and you'd want this to be 25%. So if we work that out, we know that 25% as a decimal is 0.2500, because again you're moving the decimal place 2 places to the left when you divide by 100. So on the chart, the z-score that goes with 25.2500, we just look for 0.2500 or as close as possible to 0.2500. It looks like that would be negative 0.67 I'm getting. Z-score equals negative 0.67. So then when we use our formula, z-score equals data value minus the mean over the standard deviation. In this case, our z-score, we're looking for what data value goes with the z-score of negative 0.67. And we don't know what the data value is, but we do know that the mean is 640. And we do know that the standard deviation is 160. So then we're going to put that over 1, cross multiply, and we get x minus 640 is 160 times negative 0.67, which is going to give you x minus 640 is 107.2. So x would be negative 107.2 plus 640, which would be 532.8. And that would be in kilometers. So most people would wait till 640 kilometers, but Zach, being an elite runner, would replace his after 532.8 kilometers. Okay, question number 5. Cars are undercoated as a protection against rust. A car dealer determines the mean life of protection is 65 months and the standard deviation is 4.5 months. What guarantee should the dealer give so that fewer than 15% of the customers will return their cars? So again, we're looking at, a normal distribution where fewer than 15% would be down here somewhere. And we would be trying to figure out what z-score goes with 15%. So 15% would be in decimal form 0.1500 if you divide 15 by 100. And on the z-score chart, looking up the z-score that goes with 0.1500, that would give a z-score of, so 0.1500 is down in the negatives, and it seems to be negative 1.04, I believe, because I've got 0.1492. Z-score, so on the z-score chart, it's 0.1492 is as close as we can get to that. So that goes with a z-score of, what did I say that was? 0.1492 is negative 1.04. So negative 1.04 on the z-score chart. So if we use our formula, negative 1.04 equals, we don't know what the data is, but we do know that the mean is 65 months and the standard deviation is 4.5. So if we cross multiply that, we get x minus 65 equals 4.5 times a negative 1.04. .68. So x take away 65 equals negative 4.68, and the x would be negative 4.68 plus 65. Which is 60.32. And that would be in months. So if you want to make sure that fewer than 15% of customers will return their cars, you have to make sure that that it lasts 60 months, a guarantee that it would last 60 months. Okay, question B says it's estimated that about 2,500 cars will be undercoated annually. The average repair on return cars is about $165. How much money should the dealer have to cover how much money should the dealer have to cover the cost of customer returns? So out of those 2,500, based on our answers in A, we have worked it out so that 15% of those 2,500 wouldn't last as long as 60 months. So 15% of 2,500 would be 375 cars would come back complaining. So therefore 375 cars times $165 for each repair would be $61,875 for customer returns. Okay, so that finishes off the examples for this section, and there's some questions here listed at the bottom for you to practice, and looks like there might be a worksheet as well. Okay.